Okay, so now we want to use the same data set as before and start writing a model and talk about linear regression when we have simplest linear regression, when we have just one independent variable and one dependent variable. So let's run this. As you saw before, this is our data set. We have the name of our serials and different variables. Some of them are numerical, some of them are categorical. So for actually this participation point for this lecture, I want you to go through all of these variables in this data set and tell me in order which of them are numerical, which of them are categorical, and mention the name of each variable, and then tell me which is numerical, which is categorical. Okay, so now we want to talk about response variable and explanatory variable. So let's say I want to see what's the relation between calorie, and let's consider calorie as y response variable, and then I want to see what's the effect of sugar on calorie, and sugar will be the explanatory variable. I'm going to use what is that? One of these packages that last time actually I showed but I didn't use. So this is the package actually. This is the package that I'm going to use. Later we are going to see more packages, and especially statistic packages. Okay, so for this package, my explanatory variable must be a two-dimensional array. So let's say sugar, so I must convert sugar to an array with two dimensions. How we'll do that? I will write down. So let's create a variable named sugars and use numpy array, and then I'm going to choose sugar from dataset. So in this way, I'm going to create a numpy array. Let's look at this array. Creating numpy array here. So this is my array. This is one-dimensional array. So I should convert this to two-dimensional array by converting sugar first of all to list. How I do that? Dot to list. Convert that to list. Then convert it to list using to list. And then what I do, I will use reshape. We have two parentheses here, -1 and 1. So this reshape help us to convert sugar to two-dimensional array. So now look at this. We have one column, yes, with different row. So it's not a 1D array anymore. Okay, so what reshape does, converts numpy array, which was a list, to two-dimensional Okay, so we must use this reshape to change it to two-dimensional array. Okay. So again, for changing one-dimensional array to two-dimensional, I used first of all NP array, then toList, and then reshaped it, right? Why do I have to do that? If I want to use this package, I must have independent variable. I must convert an independent variable to 2D array. Okay, so what I'm going to do here now, just to show you what happens, I'm going to print type of sugar. Now you see it's ND array, and then I'm going to print sugar's shape, and then you see now we have two dimension. Okay, so now what we are going to do to begin creating our model, I'm going to write down model equal to SKLM. So what is that? It's a brief name for this whole package, linear model. Dot, there is this method in this package, and then we can directly at the same time fit the model by using fit function. In this model, our x variable is sugar. I cannot use this. Why? Because I changed sugar name. I changed it to two-dimensional, and now this one is two-dimensional. This one is not two-dimensional. Remember, this is directly coming from the data set, but this one is the converted one. I am fitting the created regression model. First argument is x. The second argument is y. Okay, so y, I can say, okay, data set calorie, how do I write down? C-A-L-O calories. Okay, so we have two arguments. So I'm fitting the model, creating a linear regression model using this package, sklearn linear model. And now I want to see some of the characteristics of this model. Characteristic of model. So how I do that, I want to print model dot, so I can get a score of sugar and data set dot calories. So this is the coefficient of determination, R squared, that I was talking about, that explained the variance of response, that explained by this model, variance of calorie, that explained by the model we created on the explanatory variable, which is sugar. So the other characteristic or attribute that I can get is the model intercept. Model dot intercept. So this is the intercept of the line for this model, for linear model. And then what else we want to know? We want to know the slope, right? Intercept of model, and then a slope of model. Because we have just one explanatory variable, which is sugar, one variable, we have just one coefficient. And look at this, it's array. Why? Because if I had 2 or 3 variables like protein or other variables together, so I would have more coefficient. For each of variable, we will have one coefficient. Do you remember? So let me show you. So this is the picture earlier in previous video I showed you. So this is the intercept, estimate of the intercept. This is the estimate of a slope for sugar, and the y variable is calorie. So imagine if I had more variables, we will have another estimate of the coefficient or a slope for another variable, if we have it. Okay, so let's go back to what we were doing. So we got the coefficient, a slope, coefficient of sugar in the model, and we call this a slope, right? This is the intercept of the model. So these are all the information we can get. So what this says now, 2.4, if everything is correct, if our model is perfect, which still we don't know, we have to analyze the residual plot of model. Later we will talk about that. So let's say everything is correct and the model is correct. The model is a linear model, intercept, y hat equal intercept plus, for example, the slope, which is this one, multiply sugars as variable, right? Let's say this is perfect. So what this explains if for 0 sugar, predicted calories. Okay, so for sugar equals 0, 2.46 multiply 0 plus 89 will be the predicted calorie. So what is the predicted calorie? So predicted calorie will be just 89 if sugar was 0, right? With x equals 0, intercept is this much, and that would be the beginning of the predicted calorie for sugar 0, because we don't have negative sugar, right? So we are not talking about negative x variable. So for sugar equal 1, the predicted calorie will be this intercept plus 2.4 slope, right? For 1 unit sugar, we have this much slope increase in calorie. For 2 sugar, we have 2.4 multiply 2 plus intercept. So if we add another unit of sugar, the predicted calorie will increase 2.46 units. So by increasing 1 unit x, by increasing 1 unit of x, which is sugar, the predicted calories will increase how many units? Slope units. What was the slope? 2.04. Okay, so now another participation point. How do you change this sentence if a slope was negative? So this is your other participation point for this lecture. So this is the participation point for this lecture. So you should explain to me and change this sentence to the way if we had negative 2.46 as a slope. Okay, so let's continue. Now we have what is a slope. Now we have what we know what is intercept. So let's talk about predicted calorie. Predicted calorie. Okay, so if you remember, I said for each of the response variable, we will have a predicted response, correct? So how I can do that? I can use this attribute, model.predict, and my x variable is sugar. So in this way, for each of, I had 77 response variable, observed response. For each of observed response, this is the predicted response. So let's go back and see what was my data set. So print the data set. And what I want to do, I want to say all the rows, but I want just calorie. I want just the column that explains the calorie, because calorie is the response now, right? Okay, so let's do this. First of all, this one is dot. Then I should have a bracket. Then let's remove this. So, okay. For example, for calorie 70, which is observed calorie based on sugar, this is the predicted response, 104. And then 120 is observed response, but this is the predicted response for that. For each of them, we have a predicted response. And you see, the value of response are different. So some of them have positive residual. If you subtract the predicted y from observed y, you will find the residual. So this is the observed response or observed calorie, and this one shows the predicted calorie. So the difference between, do you remember what was residual? Is equal to observed y minus predicted y. So if we subtract each of these from the observed y, we will get the residual. Okay, so let's go back and continue what we were doing. So let's say I want to see what is the predicted. Let's say I like to know what is the predicted calorie when sugar is 20. Why do I say sugar 20? Let's look at the sugar. Where is sugar? Here, sugar is a value between 0 to 14. Or if we go up, we here have it kind of, we described sugar statistic. Sugar has a minimum of -1. Oh, wow, -1. Some of the cereal have -1 sugar. Means if you eat them, you will burn sugar. I don't know. Someone explained this to me. And then maximum is 15, right? So this statistic is good because now I could come back and see what's going on, what's the minimum and maximum. So when I go here, I want to see, okay, so the maximum sugar was 15, right? So let's see what is the predicted value of response for sugar when sugar is 20. So this, first of all, if you remember, this should be a 2D array, right? MP dot array, and then 20 predicted response for sugar when sugar is 20. And then I'm going to reshape this, reshape -1 and 1. What happened now? Okay, so this is the value. Let's create a predicted calorie when sugar is 20, right? So now you will see that. Let's add okay, now it's here. Okay, so the calorie will be 139 predicted calorie if the sugar is 20. So I'm assuming that all these predicted values for the calorie, 124 is the highest here. So all of them must be lower than this one because we saw a positive slope between sugar and calorie, right? As sugar increases, calorie increases. And this is one of the unit of sugar which is not in the data set. So it was the way above maximum, right? So the calorie must be way higher than whatever we predicted for a regular data set. Okay, so this is the way we predict some value. Now that we know these kind of things, actually let's, before I continue, let's talk about R square. Look at the R square. R square is 0.316, right? We didn't describe R square here. R square explains the least square regression line, the variation of calorie in the based on the model on explanatory variable. This R square is a I can say a really low. If we want to explain this, we will convert this to percentage. We will say, okay, 32% of variation of calorie is explained by least square regression line on the X, which is sugar, right? So R square can be low if we are underfitting the model, means we don't have enough explanatory variable to explain the variation or create the model, right? And then also it can be low when we have a kind of our residual are very variable and the variability of residual increase or decreased in the model. So this R square here is kind of problematic, and we should investigate and see how we can improve the model, kind of. Okay, so the other package I want to introduce to you now is the statistic package. And the other package is, let me create a raw cell. Another package is stats models. Okay, so with the stat models, using this package, I'm able to draw a graph of residual versus fitted values. So again, what was the residual? So the observed value response minus the predicted response, right? And then we know that for each observation we have a residual or error. So if you have I individuals in the data set, we'll have E1, E2, E3 up to EI residual for each observation, right? And then with all these points, like the way here we had all these points on a scatter plot, we will have as many as these points in residual plot. So we'll have that many points in the residual plot to create a residual plot. So the residual plots help ensure that our regression model is valid. So to find unwanted patterns, it's very important to check the residual plots of a certain explanatory variable versus the response. Actually, whenever we fit the model, okay, so there are some assumptions actually that must meet when we use regression analysis, like let's say normality and variability, all of this, and etc. So to make sure all these assumptions of linear regression met, we must use residual plot to check this assumption. if we violate the assumptions, then we are risking producing the reliable results. So we cannot trust our result if we violate any of assumption. So to make sure we are not violating any assumption, we must create a residual plot. Okay, so next time we will talk about the stat model package that creates a residual plot and gives us some data summary for this data set we have.